Alright, hi and welcome. So in this video, we're working through logarithmic functions. I'll have my completed notes posted, or I also have a blank version of these if you want to work through them with me, whatever's best for you. So in the last video, we talked about exponential functions, and these are going to help us really determine what a logarithmic function is. So I just want to remind us of what the general graph of an exponential looks like. It basically either has growth, where we have this shape like going up, or we have some decay. So that would be like an always decreasing graph. Oops, and that's not a very good example. Okay, there we go. So what I want to comment on here is that if we look at both of these graphs, exponential functions, if these are exponential functions, they're one-to-one. So they pass both the vertical and the horizontal line test. All of the inputs have only one output, and all of the outputs have only one input. So I'm going to say that exponential functions, which are like these ones here, these graphs, are one-to-one, and having that one-to-one property means that they're going to have inverses. So exponential functions are one-to-one, and one-to-one means that they have inverses. And the inverse thing that we're looking for, the inverse function, is going to be our logarithm. Okay, so this is our motivation basically, is that we have these exponential functions. If we're able to apply an exponential function, we want to be able to undo it. We want to be able to have an inverse. So let's go ahead and define our logarithm, which we're going to pick specifically as being able to undo or provide an inverse for exponentials. So we define the inverse of an exponential as a logarithm. To be a logarithmic function, maybe that's how I would say it. So when we talk about logarithms, I really think like this is where they come from. You know, maybe they were used in a different way, but like in my mind, this is how I make sense of it, is like we have exponentials, we want to be able to have an inverse for them. That's what logarithms are. So if we have a statement like f of x equals a to the x, that'd be our exponential. Then its inverse, f inverse, which is the logarithm, we're going to write as log, for logarithm, base a of x. So again, we read that log base a of x. And so what's happening here is we're taking the base of the exponent, that's the a to the x, and it's becoming the base of the logarithm. So it's like telling you what the output was that came from that exponent. So we'll talk about this more. I don't think that was actually a very eloquent way to say that, but just know that this is how we're defining the inverse of just a to the x. So if a to the x, then log base a of x is the inverse. So that's our logarithm. We'll do a lot more with logarithms, but that's like the basics of where it comes from. So what's going to help us first, just to explore a little bit about like how logarithms work, is to use this idea of inverse. So in the past, we talked about how if two functions are inverses, they have this certain property. So let me go through that. So we know that inverses have a special property. And the property is that we can compose the functions together and we should just get out x. So we should be able to do f of f inverse, and we should be able to do f inverse of f, and just get x out. So that's what should happen, is we should be able to do the inverse both directions, the composition, and just get out x. So what I'm going to do is like a little bit of work in between here to show us what that really means. So for us, if our function, so let's do the f of f inverse first. If our function is a to the x, and we're inputting the log base a, this is telling us that a to the log base a of x equals x. So anytime you have a to the log base a, all that happens is just that x value comes out. So we'll see this in practice in just a moment. This is just where we're starting. Then we can do this the opposite way. So if our input is a to the x, then this is log base a of a to the x. Here, if those bases match, so log base a and the base of the exponent, then that x value just comes out. So this is just like how we're defining this to work. This might be the first time you've ever seen logarithms. You're sort of like, hey Claire, what the heck? Like, what's going on? So hopefully I can explain this to you as we do some examples. The idea is just like you might like divide as an opposite of multiplication, or you might subtract as the inverse of addition. We're just going to write this log thing as the inverse of exponentiating. Exponentiating. So before I show you some examples, I just need to tell you some special logarithms that we have. So just like we talked about the Euler's number for the exponentials, we're going to have something similar for logs. So I have a little bit of room here. I think I'll fit it in. So our special logs, or special logarithms, so if we have base e, we write that as ln. So natural log of x, ln of x. That's if we use a special base e of our log. So this is anytime we're doing the inverse of e to the x. So inverse of e to the x. And we write this as natural log. I'm honestly not sure why the word uses the word natural. I think it has something to do with the Euler's number. That's actually kind of interesting. I'm not sure why it's called that. But we usually write it as ln, and I sometimes will write it like more in cursive just to like kind of show that it's an L. So ln. If you have a button on your calculator that says ln, that's always what it's doing. It's just using the base e. That's just shorthand so we don't have to write the log base e all the time. And then the other one we have is base 10. So anytime there isn't a base written, and it's just log of x, you can assume that there's like a hidden base 10. And the idea here is that like our counting system that we use, at least in like Western society right now, has a base of 10. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we start counting 10 more. So we do 11, 12, 13, 14, 15, all the way up to 20. And like the numbers repeat themselves every 10 basically, right? So that's why base 10 is sort of our standard way of doing things. And so if there's no base written, you can assume it's base 10. So this is the inverse of 10 to the x. And this is our common log, is what I would call it. So it's sort of our common way of counting, so it's our common logarithm. Okay, I think I'll make just one more note really quick. This probably isn't going to mean a whole lot to you right now, so bear with me. I'm just kind of giving you these notes so that you have them, and we'll use them as we work through the examples. So just one more thing to note. So this is a note. If we have any log base a, and we take of 1, we could rewrite 1 as a to the 0. Let me do that quick. Remember, because a to the 0 is always 1, so anything to the 0 power is always 1, so we could rewrite 1 as a to the 0. And then these bases here match, so we're in this case where the bases are the same. I'm trying to really highlight this. And so the bases are the same, and so we just get out x. So this is always going to be equal to x. Oh, sorry, wow, that is not what I meant. It's always equal to the exponent, which in the thing I wrote was x, so here it's 0. So that 0 is what comes out. Man, I really didn't do that one right. So here, log base a of 1, the log of 1 is always 0. That's really all I'm trying to say, and it's because of this property. It's because a to the 0 equals 1, and so log base a of 1 is 0. So we'll see this quite a few different ways. I just want to tell it to you now in case you like get to a prob and you're like, I think this one's special, I don't totally know what's going on. You can remember like, oh hey, Dr. Clark gave me that note that the log of 1 is always 0. So that's just something to keep in mind. Okay, all right, I've rambled a long time without being able to do some examples. So what we're going to do is use these two properties that I wrote up here based on well, the inverse property. So we're going to take these with us into the next example problems. This is just saying that if you have the base of the exponent and the base of the log being the same, they kind of cancel each other out. They kind of undo each other, as you would hope inverses would. This is really going to help us do these problems where we're just evaluating or simplifying. Okay, so let's go through these. We're just practicing using these two rules to really understand how logarithms and exponentials interact. Okay, so our first problem, problem A, we have 3 to the log base 3 of 5. So here I'm seeing this matches up with my first formula. And I guess I won't really write it like that. So I have the 3 as the base of the exponent and the 3 as the log. So all that comes out is this 5. So 5 is my answer here. And yeah, it's really hard to write over that without kind of muddling it up. So the 3 and the log base 3, they basically undo each other, and we're just getting that 5 out as the answer. Okay, next we have e to the natural log of 2. So remember, natural log, as we just mentioned, that's log base e. So here the base of the exponent and the base of the log, we have e and e. Those mean they will undo each other, and so our answer is just 2. All right, now we have log base 10. So as a comment, like, you could really be typing all these in your calculator, but that's kind of boring. So we're trying to practice like some fluency with these things to be able to understand the properties. So you can always calculate it on something if you really need to check, but I'll try to write and like tell you, don't use a calculator. We're just trying to do this by hand. So to unpack this one a little bit, when I have log and nothing's written, that's like a base 10. So I'm really looking at log base 10 of 10, which is now matching up to my second property a little bit better. So what might help is to remember that it's really 10 to the 1. So if it's not like any exponent, there's always like a 1, you just do it one time. And so the answer here is 1. So log base 10 of 10 is just 1. All right, so something similar should follow when we do 100. So this is log base 10 of 100. And now I want to think of how can I write 100 with a 10 instead? We really want to use our property with the bases being the same. So I'd like to rewrite this as 10 to the something so that I can use my property array of a and a. So 100 is 10 squared. So all I'm going to do is write 100 as 10 squared. Then my answer is 2. So those bases now match. Log base 10 of 10 squared will just give me 2. Okay, so hopefully you're starting to see we really are just trying to match it up to our two different like formulas that help us simplify. I will move them down here. We'll keep going. Okay, next we have natural log of e to the 9. So what I'm going to do is just write out log base e just to really reinforce that. Then the e's are going to undo each other since those bases match, and I'm just left with 9. So far I'm giving us pretty easy ones. I guess not like that easy, but just easy enough that we're not trying to like do a ton of extra work to simplify these. We're really just getting some fluency with the basic definitions. So this might not like feel easy at first if this is the first time you're doing it, but just know we're really trying to start with the most basic examples to get some like practice, I guess. I don't want to be one of those teachers who says things are easy, so sorry about that. Okay, next we have log base 6 of 6 to the negative 3. Here our bases already match, so 6 and 6, so our answer is just negative 3. Not too bad. Okay? Yeah, actually that was not bad, but so there's a negative exponent here, but we just still took out negative 3 as the answer. Okay, now we have log base 2 of 8. So here's where I'm not immediately seeing how the bases match. I'd really like this to be log base 2 of 2 to some power so that I could just take that power out like we did in the last example where the 3 just came out. Sorry, the negative 3. So when you do enough of these, you should kind of have this in your head. So like for me, I see 8 and I'm already thinking that 8 is 2 cubed. So 2 times 2 times 2 is 8. And so here I can rewrite 8 as 2 cubed. So 8 is 2 cubed. Now my bases match that log base 2 of 2 to the x. or 2 cubed here. And so my answer is just 3. So I had to do this little rewriting and I got 3 out. All right, let's do it again. Now we have log, here it's base 10 since nothing's written. And we really want this to be 10 to some power so that we can use our property. I see 1 over 10, so that's actually the same as 10 to the negative 1. Remember, we can move that number out of the denominator into the numerator and the exponent becomes negative when we switch them. So here the answer is just negative 1. All right, and then we just have our last 2 here. So I already spoiled this one a little bit. I said log base a of 1 is always 0. And let's just go through that again to hopefully really solidify it. Remember, log base a, we can write 1 as a to the 0 power. And then those bases are the same, so we're just getting out 0. So it doesn't matter what the base a is. We don't even need to know. We're just getting 0 as the answer. And then this is just your reminder that a to the 0 power is always equal to 1. So a to the 0 power is 1, and then log base a of 1 is consequently 0. All right, so these last 2 statements here where we have the log base a of 1 equals 0, and then we also rewrote it, or it's like really similarly written as an exponential. This is what we're going to talk about doing next, is converting between logs and exponentials. Oh, I spoke too soon. We got to look at a graph first. Okay, that's good. So, all right, we have gone through some examples of how to simplify logs. So hopefully we're starting to see how the inverse property works. Remember, we have our special logs, which are natural log and common log. And we have our definition, which is that a logarithm is an inverse of an exponential. So let's go through a graph really quick. I just want to get you to see the general shape. We could just do this on Desmos, but I think it's kind of, it's like interesting to look at substituting in some points and graphing it. So we're going to go ahead and substitute in a bunch of points. I'm going to use powers of 2 to help me out. So I'm going to just choose points that I know are going to work well, and hopefully you'll see why in a moment. Oops. So I'm doing powers of 2. So I'm doing 2 to the negative 2, negative 1, 0, 1, 2, 3, 4. And then when we start to write out these, we should see why this is helpful. So we're doing log base 2 of whatever our input is. And we do this for all of them. So I'm going to actually just write them all out really quick. We do log base 2 of our input. And honestly, like if you're doing this, you don't need to write all this out. I'm just kind of doing it so that we really have a complete way of looking at it. And now let's use the properties we just practiced to simplify these. So if we have log base 2 of 2 to the negative 2, we should be getting negative 2 out, just that exponent. Then negative 1, 0, 1, 2, 3, and 4. So I kind of set this up so that the outputs would work this way. The log base 2 of 2 to the power just kind of takes out that exponent and tells you what it is. So negative 2 through 4. And it's going to be helpful to us if we know what these numbers really are to graph them. So 2 to the negative 2 is like 1 over 2 squared, which is 1/4. 2 to the negative 1 is like 1 over 2, 1/2. 2 to the 0 is 1. And then we have 2, 4, 8, 16. So these are my points, and let's go ahead and plot them. Okay, so my first point is 1/4 negative 2. So 1/4 negative 2, just kind of guessing honestly. Then we have 1/2 negative 1. We have 1, 0. We have 2, 1. Then we have 4, 2. 8, 3. And 4, 16. Oh, sorry, 16, 4. I read that backward for some reason. And so our shape of the graph is looking something like this. Wow, that's pretty good. All right, So this is our logarithm. Remember, it is the inverse of the exponential. And so we should be seeing kind of a similar graph. It's just that the inputs and the outputs are swapped. So we'll get to that in a second. I don't want to get too far ahead. Let's talk through the domain, range, vertical asymptote, and inverse. So the domain here, we're starting, well, we don't have any negative numbers, so we're really going up to 0 and then to infinity. Wow, I don't know why I said that. The domain is from 0 to infinity, not including 0. So this is sort of an important conclusion here, that we can't take the logarithm of a negative number. So the domain is from 0 to infinity, and sort of like a conclusion is that like no negative, or like only positive inputs is maybe how I would say it. Only positive inputs to a log. So if you try to input like into your calculator log of -2 or log of 0, it's just going to be undefined. So we can't input negative values. And you can hopefully believe me that I didn't just like pick the right points because of this this asymptotic behavior at 0. Where it's sort of like getting closer and closer to 0 but never reaching it. And that's similar to how it worked for exponentials, just with the opposite. So the inputs and outputs were swapped. Okay, then the range is going to be all real numbers. So we have all possible negative and positive outputs. And again, remember the domain and range, when you go to the inverse, they switch. So you should be seeing the same domain and range. Well, sorry, the domain of the log is the range of the exponential. And the range of the log is the domain of the exponential. So those just swap. Okay, now we're going to have a vertical asymptote instead of a horizontal one. So here the vertical asymptote is at x equals 0, and that's this vertical line here on our axis. That's our vertical asymptote. So the horizontal asymptote we had in the exponential now becomes a vertical asymptote in the log. And here, if we're looking at log base 2, this corresponds to the inverse function 2 to the x. So that is the exponential that goes with this log, is 2 to the x. Okay, so that's just a little bit about what the graphs looks like. I just want to make sure you've sort of seen that and can start to think a little bit about how it works as the inverse of the exponential. So now we're going to get to that converting that I really wanted to talk about, and you're getting a little sneak peek of the first problem here. So we like to convert between exponentials and logs in order to help us solve problems, like solve equations. So you can imagine if you're trying to solve for x in an equation, you might want to be able to add or subtract numbers to the other side. You want to be able to multiply or divide numbers around in order to isolate x. We need to be able to do the same thing with exponentials. We want to be able to sort of like go from one to the other by doing the opposite operation. So the way I'm going to illustrate this is by saying, let's say we started with a to the x equals c. I'm going to try really hard to color code this because I think it will help. Let's say I started with this and I wanted to solve for x. What I could do is apply a logarithm to both sides. So I could apply log base a to both sides. That's my inverse. So it's like adding something to both sides or dividing something from both sides. We're just going to apply a log to both sides. So this looks like log base a. Oh no. Log base a. Oh gosh, I'm trying so hard to do the colors. Of a to the x. And then we do the same thing on the other side. Log base a. And now it's of c. All right, then if we look at the left-hand side, we can use our property that where those two bases match, the log base a of a to the x, we're just getting x. So this is really x equals log base a of c. So we solved for x by applying a log and then using our property that helped us simplify. And this got our x value out of the exponent and now into just the equation, like as a base. So a to the x equals c, we rewrote this as x equals log base a of c. So this is our general way we're going to convert, and I actually just like to write out like a really simple statement of how this like happens, so we can just not have to do this middle step each time. So in general, and I'm going to replace x with a b value. If we have a to the b equals c, then this is equivalent we can rewrite this as a log. So we have b equals log base a of c. So we can just swap between the exponential and the logarithm anytime we want, and these are equivalent statements. Whew. Okay, so this is sort of one of our like main conclusions about how logarithms and exponentials are inverses that we're going to use to do our conversions. So let's go ahead and try this on a few problems. All right, and let me just make sure, I'm pretty sure this is the last thing we're doing. Heck yeah. So we're just going to practice converting logarithms to exponentials or vice versa. So here we're starting with an exponential and we want to convert it to a logarithm. So the way that I always try to like, I don't know if memorize is the right word, but like make sense of this rule is that the base of the exponent, the 3, is going to become the base of my log. So my final answer should have a log base 3 in it, since that 3 is the base of the exponent. And I'm kind of just matching that up to my formula on the top of the page here. So then the b value here is 2, that's the exponent. And then I'm taking log base 3 of 9. And this should hopefully make sense, because if you really quickly thought of 9 as 3 squared, you can see that the 3's are canceling and we're just getting out 2. So it like kind of follows what we think it should be happening. So 3 squared equals 9 is the same as 2 equals log base 3 of 9. These are equivalent statements. All right, now we have 10 to the negative 1 equals 1/10. We're going to rewrite this. So again, I like to kind of start with the fact that we're using the base of that exponent, so log base 10. I'll write it here even though we don't really have to since it's just base 10. Then the exponent is my b value, so negative 1. So negative 1 equals log base 10 of 1/10. And that should make sense, because if we were to rewrite 1/10 as 10 to the negative 1, that negative 1 would be the answer. Okay, and just a note, you could write this without the base at all. So you could write negative 1 equals log of 1/10, just because if we don't write the base on the log, it's implied to be 10. But honestly, it doesn't hurt to just write the 10 if you want. Just good to know that some other people might not write it, so you'll need to know how to like tell which one it is. Okay, let's keep going. So now we have e to the x equals 20, and we want to write this as a logarithm. So again, the base of the log is the same as the base of that exponent, so I'm looking at log base e. Then that exponent is my b value, my answer, so x, and that's equal to log base e of 20. And for this one, it really is more common to write natural log, so that's probably how I would personally write this. I'd write x equals ln of 20. Log base e is ln, which is our natural log. Okay, I'm going to scroll past our rule and really hope I can do this without it. So now we're going the other direction. So we have log base 2 of 64 equals 6, and we want to write this as an exponential. So again, I'm going to start with the base of the log is the base of the exponent. Then that exponent is my answer, or my 6 here. So 2 to the 6 is going to be equal to 64. And that is a true statement, so I feel good about that. Okay, so we've just switched between the two. And again, I'm just using this form, so you can always go back to this. So log base, this b equals log base a of c, we can rewrite it as a to the b equals c. Okay, now we have natural log of 1 equals 0. So I might just take an extra step and remind myself that this is log base e of 1. So when we go to do this, e is going to be the base of my exponent. Then the 0 is my exponent, e to the 0, and that's going to be equal to 1. So I'm just like moving the numbers around appropriately. Honestly, this is something that when I learned it at first, I was like, this seems kind of like magic. I don't really know what's going on. But what helps me is just to remember that we defined the logarithm to do this. It's not like somebody just like went out and like found a logarithm and then like decided that's what it did, or realized it's what it did. Like, this is what we've defined it to be. At least I don't think logarithms existed out there. We found them. I totally think some math exists out there and maybe we found it. Well, I think that. But this one, at least, we've defined the logarithm to do what we want it to do, and it's specifically to reorder the values in the exponent in this way and to like do the inverse. Okay, we're at that last example. Let me not talk too much. So now we have log of 100 equals 2. I like to take a little step and just remind myself that when it doesn't write the base, that's base 10. So this is log base 10 of 100 equals 2. Then the base of that log is the base of my exponent. That 2 is the exponent. So I have 10 squared is equal to 100. And there we go. That's how I rewrite it as an exponential. So okay, what we've done is we've practiced converting between logs and exponents by using this property. We found that property by thinking about applying a logarithm to both sides. So honestly, you can always do this if you forget what the property is. You can remember a log helps me undo an exponent, and so I can apply it as sort of the inverse. Then we also went through a graph where we talked about plotting some points. We picked smart points that we knew how to plug in. Then we did some examples, or we started with some examples where we used this inverse property in order to simplify some things. And then at the beginning we had started with just some notes. A note that log base a, any base of 1 is always 0, so log of 1 is always 0. Then we went through some special logs. We had the natural log and the common log, and we had our inverse properties. And there we go. So that is it for logarithmic functions. Thanks so much for watching, and I will talk to you in the next one.